There are also trends in electron configurations, in magnetic properties, in ionic radii, and ionization energies. What we know is when an anion forms from an atom, it does so by gaining electrons, right? And so we're adding electrons to the electron configuration. When we form a cation, we're removing electrons. And generally, we're removing all of the valence electrons. So I think of that as being, if you think of the atom as being like an onion, where each layer of skin is like a principal quantum level, when you make a cation, you're taking this partial outer level, this damaged outer skin, and you're peeling it off. Is that going to make the onion bigger or smaller? It's going to make it smaller. Cations are smaller than their corresponding atoms. For an anion, it's like taking that skin and growing in the missing piece. And so it actually gets larger. To predict the electron configuration for main group cations, you just remove ions in reverse order of filling. So for aluminum, it fills in this order: 1s, 2s, 2p, 3s, 3p. And so you just reverse it and take off this 3p electron and then the 3s electrons. And then you end up with this electron configuration, which is the same as neon. For transition metals, you always remove the valence electrons first, even if that isn't the last place they got filled. So here's the electron configuration for iron. It's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d6. But the valence electrons are the 4s. Those are the two that come off first. So if we look at the Fe2 plus ion, it's lost those 4s electrons, but it still has the 3d6. So you take the valence electrons off first. If you go one further and form an Fe3 plus ion, you're going to then remove one of those 3d6 electrons, and you'll end up with this. Any questions? Have you ever noticed that some metals are magnetic and others are not? Aluminum is not magnetic, but iron is. And it has to do with the electrons. An atom or ion is paramagnetic if it has unpaired electrons in it. It will be attracted to a magnetic field. It will be magnetic. You can stick a magnet on it. Those that unpaired electron, or sometimes they have more than one unpaired electron, generates a magnetic field because of the spin of the electron. So it's got its own little magnetic field. What we call a diamagnetic atom, all of the electrons are paired, and those substances will not be attracted to magnetic fields. They will not interact with magnets. In fact, they're slightly repelled by magnetic fields. So let's look at the electron configurations for these two ions and predict whether they're paramagnetic or diamagnetic. So cobalt. Well, cobalt has 27 electrons. Let's use the noble gas electron configuration. So we'll start with argon. And then what comes after argon? 4s2. 3d7, right? 1, 2, 3, 4, 5, 6, 7. Okay, so if we make a cobalt 2 plus ion, what electrons are we pulling off? The 4s electrons are getting taken off. So the orbital diagram for the valence electrons started out like this. right? 4, this is 3D, and this is 4s. And we're losing the 4s electrons. So this is the orbital diagram for this cobalt ion. Does it have unpaired electrons? Yes. So is it paramagnetic or diamagnetic? Paramagnetic. Let's look at nitrogen. So nitrogen is, well, writing 1s2 or helium doesn't really matter, does it? So just nitrogen atom would be 1s2, 2s2, 2p3, right? If we make a nitride ion, we're adding 3 electrons. So we're going to have 2p6, right? And so if we look at the valence electrons, we've got the 2s and the 2p. And are there any unpaired electrons? No. So this one is diamagnetic.
Why don't you write the box for 1s2?
That's a good question. Why didn't I write the box for 1s2? All of the core electrons will always be paired up.
Okay.
Yeah, they'll always be paired up. So we don't need to worry about them at all. Just looking at the valence shell. Okay? So trends in ionic radius, I kind of alluded to this earlier. I am going to stop eventually. Cations are much smaller than the neutral atoms. And here we show the atom and its cation. And you can see that the difference is quite significant. What's happening here is that we're taking off that outermost layer, and we have a higher effective nuclear charge because we lost the valence electrons. And so the new valence electrons are part of the core, previous core, and so the effective nuclear charge goes up when that happens. And so we have 2 effects causing the cation to be much smaller than the neutral atom. Anions are much larger than neutral atoms. So we're adding electrons, and this we are lowering the effective nuclear charge. So they're going to be much bigger. This one, I think, is pretty easy to remember because you think of, well, if I'm taking electrons off, is that going to make it bigger or smaller? Well, duh, that's going to make it smaller. If I'm adding electrons onto the outside, that should make it larger. Isoelectronic ions. We can have ions of different elements that have the same number of electrons. So these are 4 ions that are isoelectronic. They all have 18 electrons, and those will all be arranged in the same way. We can predict the size trend within this by looking at the nuclear charge. So sulfur has a plus 16 protons. It's got 8 valence electrons, 10 core electrons. The effective nuclear charge is going to be 6. All of these have 8 valence and 10 core electrons. So this is going to have a plus 6 charge, effective nuclear charge. This is plus 7, plus 9, and plus 10 effective nuclear charge. And we see that as the effective nuclear charge increases, the radius decreases. It's 99 picometers down from 184 picometers. That's almost half. So we should be able to do things like this. Choose the larger atom or ion from each pair. So which is bigger, potassium atom or potassium ion?
Okay.
The potassium atom is. Because potassium ion is positive, it's lost electrons. That makes it smaller. Fluorine or fluoride? The fluoride is larger because you add an electron. Adding electrons on the outside is going to make it larger. Calcium ion or chloride ion? So chloride has 18 electrons, and calcium ion has 18 electrons. These are isoelectronic. So now we want to look at the charge on the nucleus. What's the charge on the nucleus for calcium? Plus 20. And for chlorine, it's plus 16. So which is going to have a larger attraction for those outer electrons, plus 16 or plus 20? Plus 20. Stronger attraction for the electrons. Is this going to be bigger or smaller than the chloride? Smaller. The stronger attraction pulls them in, so the chloride is bigger. Ionization energy. This is how much energy is needed to remove an electron from an atom or from an ion in the gaseous state. It's always a positive. It's always an endothermic process pulling electrons off. So if we take we usually do this for metals, but here's our atom, and you have to add a certain amount of ionization energy to pull off that first electron. And then taking that +1 ion and taking off a second electron, you're going to have to add more energy. The second ionization energy is going to be larger than the first because we've already pulled one off, and it's going to be harder and harder as we continue pulling them off. And what we see is that that first ionization energy, as we go down a group, like looking at the noble gases, helium, neon, argon, krypton, xenon, as we go down a group, it gets easier and easier to pull an electron off. And I have a politically incorrect analogy for this. So you've got a mom with 2 kids who goes to the fair, and you've got a mom with 6 kids who goes to the fair. Which family is it going to be easier to kidnap a child from? The one with 6. You cannot possibly hold on to 6 children, right? They've got longer leashes, they're just kind of around you, but it's easier to snatch one. That's how I think of taking electrons. The atom gets bigger and bigger. There's more electrons, they're farther away from the nucleus, it's easier to pick one off. So as the atom gets larger, it's easier to pick off an electron. We generally see that first ionization energy increases as we go across a period. It's kind of a jagged line, but generally it's increasing. This is going across a period, going across a period, going across a period. It's increasing. What's happening with the size is decreasing. As you go across a period, the atom gets smaller, and so it's going to be harder to pull it off. We also have issues of effective nuclear charge. So here we see the trends as we go down a group. It becomes easier and easier to ionize them. As we go across, it becomes harder.
It's just the reverse of the atomic radii.
Yes. It's opposite. It's the opposite trend to the size. The other way you can remember this is, well, fluorine. Does fluorine really want to become a +1 ion? That's what pulling an electron off does. Does it want that? No. Does sodium or lithium want that? Yeah, they'd kind of like that because that would give them a noble gas configuration. It's much easier to pull one off of here than over here. Yes?
So why earlier did we say then that chlorine, between chlorine and calcium, you said it was calcium was bigger, but chlorine was bigger?
We were comparing a chloride ion with a calcium ion. So they had the same number of electrons. Then it has to do with the effective nuclear charge as to how big it is. Oh, man. Okay, later.